You know that feeling when you bite into a lemon and your whole face just puckers up? Or why soap feels so slick and slippery in your hands? Well, that's not magic. It's actually some really cool chemistry. Today, we're going to pull back the curtain on the invisible world of acids and bases, which, believe it or not, is happening all around us all the time. So, lemons, batteries, and soap, what could they possibly have in common? I know it sounds like the beginning of a weird joke, right? But there's a single, fundamental chemical idea that ties them all together. And if you stick with me, you'll know exactly what that is by the end of this. All right, so here's the game plan for today. First, we'll get to know the basics. What exactly are acids and bases? Then we'll see them in action, making things happen. We'll check out this awesome thing called neutralization, figure out how to measure their strength using something called the pH scale, and then, this is the best part, we'll connect all of this to your everyday life. Yeah, even down to the salt you sprinkle on your fries. Okay, let's dive right into part one. What are acids and bases? Time to meet the fundamental players in this whole chemical story. So first up, we've got acids. You're already familiar with these, probably more than you think. It's that sharp, sour taste in lemons or vinegar. Now in a lab, their classic party trick is turning blue litmus paper red. But here's the real secret sauce. When you put an acid in water, it releases these tiny things called hydrogen ions. We call them H+. And trust me, that little H+ ion is the key to, well, pretty much everything an acid does. All right, and for every acid, there's an equal and opposite base. Bases are the ones that feel kind of slippery or soapy, like, soap. They do the exact reverse of acids with litmus paper. They turn red litmus blue. And their secret weapon in water, they release hydroxide ions, or OH-. Oh, and a little bonus fact for you. When a base can dissolve in water, we give it a special name. We call it an alkali. Now, it probably goes without saying, but please don't go around tasting or touching random chemicals to see what they are. That's a terrible idea. So how do we tell them apart safely? Well, we use something called indicators. You can think of them like tiny spies or chemical detectives. They change color to give us a signal. Some are totally natural, like litmus, and some are man-made, like phenolphthalein, but they all give us a clear visual clue. Okay, check out this table. It's basically a chemical fingerprint chart. See how hydrochloric acid, which is a classic acid, always turns blue litmus red, and phenolphthalein stays colorless. But now look at sodium hydroxide, a base. It does the complete opposite, turns red litmus blue, and makes phenolphthalein go this amazing bright pink. You see? Every substance has its own predictable color change pattern. All right, so we've got a handle on how to spot an acid or a base. Now for part two, chemical reactions in action. What happens when we mix them with other stuff? This, my friends, is where the real fun begins. Okay, picture this. We're in a lab. We take a few little pieces of zinc metal and drop them into some hydrochloric acid. Right away, you see it, fizzing, bubbling like crazy. We can actually catch that gas in soap bubbles. And then, if we bring a lit match or a candle near one of those bubbles, pop. That's the sound. That signature pop is the unmistakable calling card of hydrogen gas. And what we just saw in that little experiment, it demonstrates a super important rule in chemistry. When you mix an acid with most types of metal, you're always going to get two things out of it. A type of compound we call a salt, and that flammable hydrogen gas that makes the pop sound. So, acids plus metals, got it. But what about when an acid meets its total opposite, a base? Well, that leads us right into our third section, the power of neutralization. And this is a huge deal. It's a reaction where these two opposites meet and, well, they basically cancel each other out. It's pretty amazing. So let's set this up. First, we take a solution of a base, like sodium hydroxide, and we add just a couple drops of our phenolphthalein indicator. And bam! The whole thing turns this brilliant pink color. That's our signal, loud and clear, that we're dealing with a base. Okay, now for the magic. We start adding an acid, just a little bit at a time, drop by drop. You can see the pink color start to swirl around and fade. A little more, and then, poof, it's gone. Completely clear. The acid has perfectly canceled out the base. What's left isn't an acid, it isn't a base, it's neutral. And that whole process, it has a name, neutralization. It's simple, really. Acid plus base gives you salt and water. Just plain old water. It's like a perfect chemical balancing act. And this reaction isn't just for labs. It's happening all over the place, even inside your own stomach right now. All right, on to section 4. So here's the thing. Not all acids and bases are the same. Some are super powerful, like the acid in a car battery, while others are really mild. So how do we measure that strength? We use a really simple but incredibly powerful ruler called the pH scale, and it just goes from 0 to 14.
Okay, so anything on this scale that's below 7, that's an acid. The rule is super easy to remember. The lower the number, the stronger the acid. So something with a pH of 1 is way, way more acidic than something with a pH of 6. And what's right in the middle? That would be a pH of 7. 7 is the magic number for neutral. Not acidic, not basic, just perfectly balanced. Pure water is the classic example. It's the dead center of the whole scale. So if below 7 is acid, then you guessed it, anything above 7 is a base, or what we also call alkaline. And it works the same way, but in reverse. The higher the number gets, all the way up to 14, the stronger the base is. So yeah, drain cleaner at a pH of 13 is a much, much stronger base than something with a pH of 8.
Okay, so this is all cool science, but why does any of this matter to you? What's the point? Well, that's what Section 5 is all about, chemistry in your daily life. We're going to take this out of the textbook and show you how pH is quietly running the show behind the scenes every single day. I mean, just think about it for a second. Tooth decay, that gets started when the pH in your mouth dips below 5.5. Ever had indigestion? That's just too much acid in your stomach. And what do? You take an antacid, which is a base, to, you guessed it, neutralize the acid. A bee stings you, that's acid being injected into your skin, which is why a little baking soda, a mild base, can help with the pain. It's even in the dirt. Plants are super picky about the pH of their soil. Seriously, this stuff is everywhere. All right, for our last section, let's talk about something you probably have in your kitchen right now. Plain old table salt. You might just think of it as something for your food, but it's actually the starting point for a huge chemical factory that makes things we literally use every single day. It's a process called the chlor-alkali process, and it sounds complicated, but the idea is simple. You take salt water, that's sodium chloride dissolved in water, and you zap it with electricity. The stuff that comes out is mind-blowing. You get chlorine gas, which we use to keep our water clean and make things like PVC pipes. You get hydrogen gas, which is a clean fuel and is crucial for making fertilizers. And you get sodium hydroxide, a super strong base that's used to make soap, paper, you name it. All of that from just salt water and electricity. How cool is that? And really, that just says it all, doesn't it? This stuff we just casually sprinkle on our food, it's actually a cornerstone of the entire modern chemical industry. It's the launching pad for countless products that literally build the world around us. So there you have it. From the pucker of a lemon to the soap you used this morning, all the way to the pipes inside your walls. The chemistry of acids and bases is always there, always working. And it kind of makes you wonder, right? What other invisible chemistry is shaping your world right this very second?